All right, it's 5:30. Let's go and get started. All right, good evening, everyone. How's everyone doing today? Not bad. Good. Yeah, good. At a Super Bowl party at my place yesterday, although most of my friends aren't actually into football. It's funny. Last week I was inviting people over to come over watch the Super Bowl, and basically all my friends gave this variation of the same response. They're like, I'm not really into football, but I'll come over to your house and eat your food. So I was like, okay, that's fine. So I just grilled a bunch of chicken and pork, and then people came over, watched. Well, only I was really watching the game, but we enjoyed the halftime show. So it kind of turned out to be a Rihanna watch party more so than a Super Bowl party. But everyone had fun, so that's the most important thing. Okay, so the plan for today is I think we have an example to finish up from last time. So we were going over our first kind of MATLAB code together. And so I want to make sure I finish that, get you guys started on the homework, because I think problem 2A on the homework ask you to modify the code. So I want to give you some hints on that. I want to talk about errors a little bit, and then we'll move on to 2D problems from there. Okay, all right. And so remember, homework 2 is out there. And so I think that's due not this Friday, but next Friday. So you still have a bit of time for that, but there is quite a lot of coding in homework 2. So make sure you're kind of looking at it, and getting started early so that you're not writing a bunch of code at the last minute. All right, and so that's all my announcements. Are there any questions I can answer before we get started for today? Okay, all right, so let's pick up where we left off. And so I'm actually going to return to the notes from last week really quick, just to kind of remind you what our goal is. Okay? So let me kind of scroll up here. You don't have to write this down. And so, I'm just going to kind of quickly review it. Right? And so if you remember from last week, the example that we were working on was this one. Okay. And so we have a diffusion equation. And so we have a second order derivative. So we have d squared phi dx squared is equal to 6x. And then we have our two boundary conditions there. We have a Dirichlet boundary condition on the left, and then a Neumann boundary condition on the right. Okay. And so what we did to this equation was we applied finite differences. And so we took that derivative term and we replaced it with the finite difference expression. Okay. And the idea behind that, we ended up with this equation right here. Okay. The idea behind that is to obtain this algebraic equation to solve instead of our differential equation. Okay. And so the way that we applied this was that, we applied finite differences. We got this kind of, you can almost think of it as like a recurrence relation. And then what we did was we applied this to every single node in our grid. Okay. And so our 1D grid, we basically took our domain, we split it up into 6 nodes, and then we applied this to as many nodes as we can. And for the boundary nodes where we couldn't apply it, we applied a boundary condition instead. Okay. And so kind of long story short, what we obtained was something like this. Okay? And so we obtained kind of a linear system of equations. So 6 linear equations for 6 unknowns. Okay? And if we put it in matrix form, we get the following. Okay? And so our next step, the next thing we wanted to do was we wanted to take this matrix system and solve it in MATLAB so that MATLAB can kind of produce this solution for us. Okay? And that's what we're kind of in the middle of. So let me go ahead and switch back to MATLAB here. All right, so this is the, okay, so this is the code that we were working on last time. Okay. All right, and so, I'm not going to go over every bit of this code again, but, we'll just kind of, just review it really quickly. Okay. The main parts of this code are, kind of start right here, where we created what I call the left-hand side matrix. Okay. And so that left-hand side matrix was the matrix that we're trying to recreate in MATLAB. And then we had the right-hand side vector, where that's where we're going to put our kind of our source term as well as our boundary conditions. Okay. And then from here, and from here, what we were doing is we were building up this matrix basically one row at a time. Okay. And so the first thing we did was the first row. And so remember, the first row corresponded to the Dirichlet boundary conditions. Okay. Then we did the second row and the third row, the fourth row, the fifth row. Okay. So all of these look very similar because these are all interior nodes. And then finally, we had the last row, which was this one here. Okay. All right. And so once we filled out the matrix and once we filled out the right-hand side vector, we're able to solve it. And so to solve a matrix system of equations in MATLAB, remember you use this backslash notation, okay, just like we talked about in our MATLAB review, and then we can solve for the result. Okay. All right. And so the last part that I did kind of very quickly at the end was I plotted the exact solution. Okay. And so you can kind of see how well our finite difference solution matches up with the exact one. And so in blue, right here, we have our finite difference solution. And in red right here, we have the exact one. Okay. And so you can see, it does a decent job. It gets the general behavior correct, but there are some errors. Okay. And so ideally what we'd like to do is we'd like to modify this code so that we can get our finite difference solution more close to the exact solution. And so, if you already looked at the homework, you probably already know that this is problem 2A. Okay, But I did want to start it because it does involve some loops and some if statements. So I kind of want to make sure that you're kind of ready for it. Okay. All right. So what we have here is, we starting from kind of the same point, we have our left-hand side matrix, okay, and a right-hand side vector. And if you'll notice, the size of these matrices and vectors corresponds to the number of nodes that we have in our grid. Okay. And so right now the size is set to 6 because the example that we're doing had 6 nodes. Okay. Ideally, we want to kind of update this code. So instead of 6 nodes, maybe we work with 50 instead. Okay. And so we'd have 50 equations, 50 unknowns, and we'd have 50 rows to our right-hand side vector. Okay. All right. And so if we wanted to do this kind of the hard way, what we would do is we'd have to basically kind of copy and paste this code, 50 times. And so you can do that, but that's not usually not the best or most kind of best way to do this. Okay? But one thing that you should notice is that we're repeating a lot of this code over and over again. And so whenever you're repeating a lot of code, the best way to do that is with a loop. Okay? And so let me go ahead and write a loop. So we'll say for I is equal to 1. In this case, we'll put it to 50 because we want to do this to 50 equations. Okay. And let's start writing the loop. Okay. And so if you remember problem 2C on the last homework, this is very similar. Okay. And so what I'm going to do is I'm going to write an if statement. Okay. And we're going to have 3 specific cases here. Okay. The first case that we're going to look at for the if statement, remember the if statement basically allows us to tell the program to do something different in different situations. Okay. And so we have to look at our problem here, look at our kind of the code that we're developing, and we have to look at which cases are different. Okay. All right. And so what should jump out at you is that the ones that are different are going to be the first row of the matrix and the last row of the matrix, right? And remember, the reason for this is because the first and last rows correspond to the boundary conditions that we're applying on the left and right sides. Okay. And so this is going to be a very common pattern. So, oftentimes you're going to have a case where you're going to handle the boundary conditions differently. Okay. And so for the first if case, let's say so check if we are in the first row of the matrix. Okay. And so the way that we do that is we know that I is counting up from 1 to 50. The first row corresponds to I is equal to 1 because that's the first row in the matrix. Okay. And then here, write code to apply boundary conditions. Okay. On the left side of the. Okay. All right. So that's the first if. Okay. The next case that's different is that when we're on the last row of the matrix, right? Because that corresponds to the boundary condition on the right. And so what we want to do is we want to check if we are in the last row of the matrix. Okay. And so of course the last row of the matrix corresponds to I is equal to, in this case, 50. Okay. Write code to apply boundary condition on the right side. Okay, so I'll let you guys fill that in. And then the else, remember the way that we use the else statement is the else is going to be every other case. Okay? And so if you're not in the first row and you're not in the last row, that means we're in all the middle rows. Okay? And we know that when we're in all the middle rows, or we're basically when we're in all of the interior nodes, the equation that we apply is the finite difference equation. Okay? So write code to apply. Okay. And I'll let you do that one as well. And so it is very similar to the code that we wrote here. It's just that you need to write it up here, and you need to incorporate the the loop index I. Okay. All right, this is the main thing that you need to develop for the homework problem 2A. And so you would of course delete all of this. Okay. So everything that we did last week in terms of directly specifying the left-hand side matrix and the right-hand side vector, you can comment that out, or you can just get rid of it. Okay. Everything else is the same. So you can compute the solution the same way, and you can plot the exact solution if you want as well. Okay. All right. I will give you one more hint to make this a bit more convenient. Okay. Because right now, we've kind of modified this code so that we can kind of solve the solution with 50 nodes. But what if we decide, maybe we want 55 nodes, maybe we want 65. Okay. And so if we want 65 nodes, we'd have to go in, and everywhere we see 50, we'd have to change it to 65, right? And so in this case, it's not that bad because it's only a short amount of code. But later on, once we're writing codes that are hundreds of lines long, it's going to be annoying to have to go and find every single instance of that. Okay? And so to help with this, you can create another variable. Okay? So I like the variable named big N, where big N can be the number of nodes that you have in the grid. Okay? And so if we replace all the 65s here with N, then what this will do is that this will update the code automatically for whichever amount of nodes that you want. Okay, so let's say that you want to solve. Let's say you want to solve this equation for 9,001 nodes. Okay, so slightly over 9,000. And so if you write the code in this way, then it'll automatically update. And so you only have to change the value of one variable, and the rest of your code will update from there. Okay, so this is kind of the style that we're going to use for a lot of the classes. So generally what you'll see me do is that I'll have kind of an upper section of the code where I define what I call kind of global. I call them global variables. Okay, and then those global variables, the way they're designed is so that you can just change their values in one part of the code, and then everything else will kind of update from there. Okay. All right, so hopefully that kind of helps in getting you started for that. Any questions on this? Yeah. I can upload it. Yeah. Yeah. Mm-hmm. Yeah. Just remind me after the class because I might forget. All right. So that's kind of your help for problem 2A. Okay. All right. So let's switch back to the lecture notes. Okay. All right, so now that we've kind of implemented our first code together, let's talk a little bit about kind of analyzing our code. Because as you saw from the solution that we got from there, our finite difference solution it wasn't perfect. It was okay. So let's talk about how do we assess, or how do we actually rate how well our codes are doing. And the way we do that is we compute our errors. Okay. All right, so before we can talk about errors, let's kind of remind ourselves kind of the goal of what our finite difference solution is hoping to obtain. And so remember, the reason we're kind of embarking on this finite difference journey is to basically solve our differential equations using MATLAB code. Okay? And so what we aim for is that we want our finite difference solution to be basically have the exact same solution as the exact one. Okay? And so we can kind of use that kind of naive definition to define a metric for the error. Okay. This is not the only error metric in the world. There's actually too many to count, but I think this is kind of the most straightforward one, the easiest to understand. Okay. All right. So one way that we can compute the error is we can take the finite difference solution. And then we just simply subtract the exact solution value. And in fact, oftentimes we have to do this on a node by node basis. Okay. And so one thing we can define is we can define epsilon. Okay. So epsilon sub I. So remember, I use the subscript I to denote, whenever we're referring to a specific node. Okay. So this kind of notation here is the error at node I. This is equal to phi from our finite difference solution at node I minus the phi exact at the same node I. So let me draw kind of an approximate graph here. For blue here, this is the finite difference solution. And in red, this is the exact solution. Okay. So that was kind of how it looked like. And so if you kind of remember, from like 10 minutes ago when I showed the graph, we had kind of low-ish errors on the left, and then as we kind of moved closer to the right, our errors grew bigger. Okay. All right. So when I mean the error, what I mean basically is you just take a difference, and so you look at maybe we could even start here, right? So at the node at the very left, we compute the difference. In that case, the difference is 0. Okay. But if we look at this location here, and we compute that difference, this difference here is the error. Okay. This difference here is the error. Okay. All right, so let's analyze the errors in this graph, and let's talk about kind of why those are occurring, or kind of the reason why those errors are there. Okay. All right, so kind of the general trend that I hope that hopefully came across in my beautiful artwork is that the errors, they're fairly small on the left-hand side. In fact, at the very left-hand side of the domain, they're really small. Whereas on the right-hand side, the errors start to get bigger. Okay, and in fact, if we continue this graph even more, the errors would probably keep continuing to grow. And so that kind of begs the question of why are we seeing these trends? So why is it that the errors are small on the left-hand side? Why are they bigger on the right-hand side? Okay. And the next question to ask is is this a trend that we can expect to see in the future as well? Okay. Is it generally going to be true that when you solve a finite difference solution, are the errors always going to be small at the beginning and then get larger at the end, or kind of what's kind of the underlying thread here? Okay. Oh, actually, I guess before we talk about that, are there any questions just on this graph or how we computed errors or anything like that? Okay. All right. So what factors are the ones that lead to these errors? Okay. All right. And so the main factor, at least here, the main factor that's at play actually has to do with the boundary conditions. Okay. Let me remind you of the type of boundary conditions that we applied for this specific problem. Okay. And so this graph is not a general one. This is the kind of actually the one from our example. Okay. And so for this specific example, the boundary condition that we applied on the left was actually a Dirichlet boundary condition. Okay. Remember, let me put the exact value. The exact expression for that Dirichlet boundary condition was that phi of 0 is equal to 1. Okay. And so why is this? So why is it that we get small amounts of errors at the Dirichlet boundary condition? Okay. The reason for this has to do with how the Dirichlet boundary condition is defined. Okay. Remember, when we define a Dirichlet boundary condition, we're saying that the solution value itself has to match a specific value. Okay. And this is true both for the finite difference solution and for the exact solution. Okay. And so if mathematically, or just the way that we're defining it, is if we're forcing those two to have the exact same thing, then it makes sense for the errors to be 0. Okay. And so generally speaking, when you're looking at a finite difference solution, looking at a simulated solution, the errors are going to be the lowest near the Dirichlet boundary conditions. And so that's a trend that's kind of true for the future. On the other hand, on the right-hand side of the domain, the type of boundary condition that we're applying there is the Neumann boundary condition. Okay. And remember, Neumann boundary conditions are conditions on the derivatives of the solution. Okay. Let me look back. The exact value of the Neumann boundary condition, I believe it was a 0. Yeah, it was 0. And so whenever you have a boundary condition that relates to a derivative, remember that's a Neumann boundary condition. Okay. And this was applied on the right-hand side of it. And so because Neumann boundary conditions, they specify the derivative of the solution instead of the solution value itself, these are naturally going to be a lot, we call them a lot weaker. Okay. And so it has a lot less influence on the value of the solution itself. Okay. And so we can basically say that Neumann boundary conditions, they affect the solution value more indirectly. Okay. Whereas Dirichlet boundary conditions, we're saying the solution has to be this. Neumann boundary conditions, we're applying the condition on the derivative, not the solution itself. Okay. All right, and so kind of the upside to this is that whenever you have a Neumann boundary condition, the errors tend to be higher in those locations. And so if we take this information and we look back at the trends that we saw from our example, okay, they start to make a lot of sense. Okay. And so if you were to reverse this, and so let's say that you were solving a problem, but instead of the Dirichlet boundary condition being on the left, we instead have a Dirichlet boundary condition on the right. And then our Neumann boundary condition was on the left. We would see the exact opposite trend. So instead of having the errors being maximum on the right, we instead here have errors that are maximum on the left. Okay. And then on the right, where the Dirichlet boundary conditions applied, we'd have low error. And so, I'll just draw a graph just to illustrate this. Okay, so maybe it looks something like this. In blue here, we have the finite difference. And in red here, we have the exact solution. Okay. And so when I ask you questions about errors, don't really get caught up in terms of, where the errors are located. Okay, because it's not always going to be always on the left or the right. It's going to depend on which boundary conditions are applied there, because the different types of boundary conditions have different effects on the solution. All right, any questions on error trends in finite differences? Okay. All right, and so that's all the 1D stuff, and so you should be able to do all of that stuff. All right, so let's go ahead and move on to 2D. And so 2D is exciting because I think this is going to be where finite difference really starts to shine. Because in 1D problems, yeah, it's fun to write your first code, and yeah, it's fun to see if it matches the exact solution. But the fact that you can get an exact solution to the 1D problems without finite differences kind of makes it seem like we're just doing this for fun. Right? And while it is fun, I'm having a lot of fun. 2D is where it starts to be useful because these 2D differential equations start to become much more difficult to solve by hand. Some of them being literally impossible to solve by hand. Okay, so let's talk about 2D. Diffusion with finite differences. Right. And so, of course, with 2D, that means we're going to add another spatial dimension. So instead of X, we're now going to consider X and Y. Okay. And so that means that our differential equations now are no longer going to be just ordinary differential equations. They're going to be partial differential equations. Okay. Okay. And so we'll start with kind of the simplest one that we can do, which is just the straight up diffusion equation. Okay? And so the 2D diffusion equation looks like the following. So we have partial squared phi, partial x squared, plus partial squared phi, partial y squared, equal to q. Okay. So this right here is a 2D diffusion equation with a source where q is our source term, and the diffusion is given by the two second order derivatives. Okay. This particular equation, and this is just trivia. Okay, so this particular equation shows up a lot in applied math. It shows up so much that it has a special name. And so this equation in this particular form is often called the Poisson equation. Right. So basically, two second order derivatives and just a random function on the right. That's a Poisson equation. Okay, so if you take one of the more advanced math classes here, so 438, 538, you've probably seen the Poisson equation. You probably know how to solve it, but it's also mentioned a lot in the literature as well. All right, a variation on the Poisson equation is if you set the source term equal to 0. Okay? And so that's another equation that we can solve. It's a little bit easier. And so a variation on the 2D diffusion equation is if we set the source term equal to 0. Okay, so this is 2D diffusion without a source. And this equation, where the right-hand side is equal to 0, this is often called the Laplace equation. And so our goal today and on Wednesday is to solve these equations using finite differences. Okay? And what you'll see actually is that the finite difference part of this is actually not that hard. Okay, so it's basically we're applying the same processes we did before. What's going to be difficult, and the reason I kind of devote a whole week to this, is that our code is going to get significantly more complex because we're diving into second dimension. And so applying the finite difference to this, it's not too bad. Okay, you can already kind of imagine what it's going to look like. And so we have two second order derivatives. And so you're basically just going to be applying our central difference scheme to both of those second order derivatives. Okay. And then you're just going to work out the terms. You're going to get a recurrence relation, and that's all going to be good. Okay. What's going to be difficult is that our codes now are going to require a lot more infrastructure. Okay. So I'll call it infrastructure, but just because I'm not sure what else to call it, but they're kind of more programming kind of structure we need in our code in order to solve this. Okay? Okay, so that's what I mostly want to talk about today. So, we're probably not going to do any finite differences today. We're not going to do any more MATLAB coding. But what I did want to talk about was kind of this extra infrastructure that we need, kind of the logic behind it and how we set it up, so that when we do start writing codes on Wednesday, we're kind of ready to go. All right, any questions on this? Okay, all right. So let's go ahead and get to it then. So let's start by talking about the domains. So let's talk about 2D grids. Okay. And so just like in the 1D case, the first thing that we have to do when we do these finite difference problems is we have to take our domain and discretize it. Okay. And so if we have a 2D domain, here we have a square domain. Maybe the X direction goes horizontally, the Y direction goes vertically. Okay. And so to discretize this, basically means to put nodes onto the domain. Okay. So we have our same domain here. But we're going to put nodes on this domain. So we're going to put nodes like this. And so let's put them in all the corners. Okay. And then let's put 2 more in each direction. With these lines mean up. We'll put nodes there as well. Okay. And so we've gone up to the second dimension. So our domains now, first thing I want to illustrate is, our domains are no longer just 1D lines. Now we have 2D kind of grids, okay, or 2D domains, and that means our grids have to be 2 dimensions as well. Okay. Of course, one other thing that's interesting is that once we go up to the second dimension, and this is true in 3D as well, the range of geometries that we have available to us are going to change too. Okay. Because in 1D, there's only one-dimensional geometry. That's a line, right? And so there's no other way we can make a line not a line, right? I guess you can curve the line, but that would be 2D. Okay? But in 2D, we can have domains that look all different kinds of ways. Okay. I will say, we're not going to do too much with this. For most of the time, we're going to work on a square or rectangular domain, but it's good to be aware of this. Okay? And all the methods that we're working on, you can apply them to all these domains as well. Okay. And so let's say that we have an L block. And so you can put grid lines on this as well. You can have like a U. Or anything else that you can imagine. Okay, so any 2D shape you can draw with this. Okay? And you would apply finite differences in the same way. Okay? The only thing that would be tricky is applying the boundary conditions. Right. But again, mostly for our cases, just to keep things simple, especially in terms of the boundary conditions, we're going to stick with rectangular domains. But just know that you could apply these techniques to these kind of awkward domains. Okay. All right. So I mentioned, before that, the big difference that we're going to have here in 2D is that we need a lot more infrastructure. Okay, so that means basically more variables to keep track of stuff and more conventions that we need to keep track of stuff as well. Okay, and so kind of the unifying theme behind all this, you may think it's a lot of busy work and it's a lot of kind of things to keep track of, but they all kind of have a purpose, right? And the purpose is to stay organized. And so we're very soon we're going to start to have way more nodes than we'd have in 1D case, way more equations than in the 1D case, way more variables in the 1D case. Okay. And so, when you're kind of dealing with the higher amount of complexity, the most important thing always is to stay organized, that you kind of know what you're doing, kind of what you're working with, and you know where kind of everything is. Okay. And so that's kind of the goal. Right. So I'm gonna basically, go over how I organize these things. This is not the only way to organize things, of course, but I find that this kind of makes the most sense to me. Okay. All right. So first, let's start with some variables that define the domain itself. Okay. All right, so we have our rectangular domain. First thing we're going to describe is the length of the domain in each direction. We have the length of the domain in the x direction, so we'll call that L sub x. Then we have the length of the domain in the y direction, so we'll call that L sub y. Okay? And so lengths are typically given in real measurement units. So L could be anywhere between like a meter, or maybe a foot, or 3 feet, something like that. Okay? So L is the physical length of the domain in each direction. And so if we have the length of the domains, we can also compute the grid spacing. Okay? And so remember, we're putting a grid on this, and so it's going to look something like this. And so from the grid spacing and the number of nodes in each direction, we can compute the grid spacing in each direction. Okay, and so we have dx. And this is going to equal to delta x. Okay. So delta x is going to be Lx divided by nx minus 1. Okay. Where nx, of course, is the number of nodes that we have in the x direction. Okay. And then we have dy, which is delta y, is equal to Ly divided by ny minus 1. Where ny, of course, is the number of nodes in the y direction. All right, so we need 2 grid spacing variables. Okay, so before in 1D we only had 1 grid spacing because that was the only direction. In 2D, we may have situations where our grid spacing is different. Okay, so we may have a much more finer grid in the x direction versus the y, or vice versa. Or we may simplify and just say that the grid spacing is the same all around. So in those cases, delta x is equal to delta y. But in case those are different, we like to keep separate variables for them. All right, any questions on this so far? All right, so fairly straightforward so far, hopefully, but but just know that we've introduced 6 variables already. So we have Lx and Ly in each directions. Okay. We have Nx and Ny, and then of course we have delta X and delta Y. Okay, so that's 6 variables already, and so that's already kind of 6 lines of code at the top of your code, and so just kind of be aware of that. All right, so let's move on to the next topic of node numbering / labeling. Okay. So whenever we apply any finite difference, whether it be 1D, 2D, or even 3D, in order for it to work, each node in our grid has to have a unique ID number. And so we took advantage of this in our 1D example, right? And so if we look back at our 1D example, our grid looked like this. Okay. And so if you remember from our 1D example, we had 6 nodes, and each of those nodes had its own unique ID number. And so in the 1D case, it was pretty straightforward. We just counted from left to right. But if you'll notice, we also use these ID numbers for something that was very important in our linear system. Okay? So in our matrix set of equations, we use these node ID numbers. We use the nodal ID numbers to basically correspond to locations in the left-hand side matrix. Okay. Again, in 1D, it was one thing that seemed pretty obvious, and so I didn't really draw any attention to it, but it was something that that was really important. Just not only in constructing the matrix, but also in constructing each of the individual finite difference equations as well. Okay, so we use those ID numbers; those are very, very important to our analysis. Okay. In 2D, excuse me. In 2D, the case is still the same, and so we still need ID numbers. But the way that we assign the ID numbers is going to be more challenging here because we're in 2D. Okay. And so in 2D, and by extension 3D as well, okay, what we need is a consistent and standardized way of labeling the nodes so that we can put our equations in the right place in the matrix set of equations. Okay. Okay. All right, and so this might also be somewhere where you may apply a different scheme, okay, and that's okay. That's fine with me. The only thing that you have to be careful is that you have to be consistent, and you have to apply kind of the same all throughout. Okay. All right, so let me do this. So let me go ahead and draw a 2D grid. And so this is a 4x4 grid. Okay, so we have 4 nodes in the x direction, 4 nodes in the y direction. And just like in the 1D case, each of these nodes needs to have its own ID number. Okay. And so the way I like to do it is like this. And so I like to start in the lower left-hand corner. Okay. Because in the lower left-hand corner, that's typically where the origin is. And I'm going to start my numbering there. Okay, so I'm going to put a number 1 in the lower left-hand corner. And the reason for that is that this is often the origin. And then from there, what I do is I like to start counting from left to right. Okay, so node number 2 is going to be the node immediately to the right. Okay. Node number 3 is going to be the node immediately to the right of that. And then 4. Okay. And then when you reach the end of the row, you go up to the next one. Okay, so node 5 is right here. Node 6 is right here. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay. So this right here is our labeled 2D. Okay. Right, so that's one way to label the nodes. Okay. But we need to be careful with this. Okay. So this node numbering, when you can kind of visually see it, it makes a lot of sense, right? So if I tell you to point at node number 10, you know exactly where to point, right? But what if I did this? What if I kind of went back up here and tell you, give me the location of node number 13, okay, without looking at your notes, right? That's a problem, right? And so if we have a different domain, let's say that we have a domain that looks like this. With a lot more nodes in the system, okay? Node number 13, may not be in the top left corner. Node number 13 may be somewhere kind of right here. Okay? And so in order to kind of properly number this, in order to properly label it, we actually need another way to refer to the nodes that actually refers to their physical location. Okay. And so let me say the nodes also and so not only does each node need to have its own ID number, there also has to be a way for us to kind of quickly and easily kind of refer to their physical location. Okay. All right, so let me do this. I'm going to draw the same square. I'm going to draw the nodes into the square. And what I'm going to draw on this grid here is a different labeling scheme that is more kind of more representative of where their physical location is. Okay. All right, and so I like to call this labeling scheme the IJ labeling scheme. So that's I, comma J. I guess the one on the left would be the ID numbered, ID labeled scheme. Okay. And what the IJ labeling scheme is that each node has an IJ coordinate. Okay. All right, so for example, and so the one in the bottom left, we'll call that node 1, 1, okay, because it's the first node. Okay. The next one, just like an XY coordinate, I'll give it 2, 1. The next one is 3, 1, 4, 1. Okay, then we come back up here. Now we're going up to row 2. So this would be 1, 2, 2, 2, 2, 3, or excuse me, 3, 2. So 1, 3, 2, 3, 3, 3, 4, 3. Right? And up here, you have 1, 4, 2, 4, 3, 4, and 4, And so this second scheme, this IJ scheme, is very much like an X. Think of it like an XY coordinate. Okay? And so with this scheme right here, we're better able to identify, the physical locations of each of the nodes. Okay. So we're going to need both. And so, we need the numbering scheme on the left so that, when we go to assemble our matrix set of equations, we have a unique ID number for each of the nodes. So the left is needed to apply finite difference. We need the one on the right because the one on the right is going to be more indicative of kind of where that node is physically located in the domain itself. Okay. And so the challenge is going to be, and this is the part where everyone gets confused, is kind of relating these two coordinate systems, relating these two labeling schemes, and kind of naturally using it when we're developing our finite difference equations. All right. Any questions on these two labeling schemes here? Okay. All right. So let's talk about how we're going to relate these together. And so we can actually relate these two labeling schemes with a very simple formula. Okay? So I call this the ID formula. And basically the way the ID formula works is that if you input or if you plug in an I coordinate and a J coordinate, that it should give you the ID number for that particular grid. Okay, so the ID formula is this. So ID is equal to, we take J, and so whatever the J coordinate is, we subtract 1 from that. Okay. And what we do is we multiply this quantity by nx. Remember, nx is the number of nodes in the x direction. And to that, we're going to add the I coordinate. All right. And so let's test this formula here to see if it works. All right. And so let's look at the example that I drew up here, right? So let's do our 4x4 grid. Okay. And so in our grids above, nx in this case is equal to 4, right? Because if we look at our grid, if we count the number of nodes, if we kind of walk horizontally across the grid, we come across 4 nodes, right? So there's 4 nodes in the x direction. And so let's use the formula. Let's use the formula to compute the ID numbers for a few different nodes. So let's do the node located at 3, 4. And I'm not even going to look at the grid right now. And so, and this example isn't even in my notes too. Okay. And so with 3, 4, we know the I coordinate is 3, the J coordinate is 4. Okay. And so let's go ahead and plug that into our formula. And so ID is going to be equal to J minus 1. So we have 4 minus 1. Okay. Multiplied by NX. And so NX in this case is 4. And then to that, we're going to add I, which is 3. So let's add these together. So 4 minus 1 is 3. 3 times 4 is 12. 12 plus 3 is 15. Mental math, baby. All right. So let's check and see if that's true. All right. So let's look at the wait. Oh, I plugged this in. 3, 4. 3, 4. What? Oh yeah, 3, 4. 3, 4 is this one right here. I did it right. Sorry. I was about to brag about my mental math skills, and then I messed up after that. Okay, so 3, 4, that's that node, right? So it's 3, you count 3 in the x direction, you count 4 in the y, and we look at the corresponding ID number, and that indeed is 15. Okay, let's do one more. Let's do 2, 3. All right, so once again, we're going to use our ID formula. And so I is 2 in this case, J is 3. Okay, so ID equal to 3 minus 1, 4 plus 2. Okay. This is 10, right? All right, so let's go back and check up on our grids. And so we look at 2, 3. 2, 3 is this one right here. We look and see that its corresponding node ID is 10. Okay. All right, so we're going to use this formula. We're going to use this formula to kind of switch between the IJ labeling and the nodal ID labeling. Okay. Once we start to form the finite difference equations. Okay. All right, any questions on that? All right, one last thing before we move on is, sometimes it's useful to compute the total number of nodes. Okay. And so I like to call this ntote. Okay. And so to compute this, what we usually do is we take the number of nodes in the x direction and we multiply the number of nodes in the y directions. Okay. So very simple. And so if we look at our previous example, we have 4 nodes in the x direction, 4 nodes in the y direction. So you take the product, you get 16 nodes overall, which is exactly the amount that we got. Okay. So now that we've kind of talked about kind of the labeling schemes, let's see how we actually apply this doing finite differences. Okay. All right. So let's take our 2D diffusion equation. And so I'm going to start with the Poisson equation. So we'll go more general. That's a Poisson equation. So we have partial squared phi partial x squared plus partial squared phi partial y squared is equal to q. Okay. Let's take this equation and let's apply finite differences to each of the derivatives in the equation. Okay. So let's start with this one. Okay. So partial squared phi partial x squared, this is a derivative in the x direction. Okay. And let's kind of note that, you know, in our labeling scheme, in particular the ij labeling scheme, the I direction is the same as our x direction. Okay. So I is same as x. Okay. All right. So remember, you know, when we're talking about 2D, and we're talking about a generic phi value phi, okay, it's going to have two indices. Okay, so our phi is going to have an I index, it's going to have a j index. Okay? And so when we're taking the derivative in the x direction, that means our derivative or our finite differences is going to be applied on the I direction only. Okay. All right. So what does this look like? So, you know, our normal second order derivative finite difference. It's like the following. And so for a second order derivative, we have phi I minus 1, or I mean phi I plus 1 minus 2 phi I plus phi I minus 1. Okay. But since we're in 2D, we have to add the j coordinate as well. Okay. So each of these phi terms is also going to have a j. And then we're going to do the same for this one as well. Okay. And so when we take the derivative of the y direction here, you know, we make note that our j direction is the same as y. Okay. All right, so we take this derivative, we have phi I j plus 1 minus 2 phi I comma j plus phi I j minus 1 all divided by delta y squared. Okay. So these two derivatives look similar, and so, you know, it's very easy to get them confused, but just kind of take note of, you know, which of the I and j indices that we're actually taking the finite difference on. Okay. So for the x direction, you know, we're taking the derivative on the I component, and for the y direction, we're taking the derivative on the j component. Okay. And then all this is equal to q I comma j. Okay. So this right here, you know, this is kind of the first step of our finite difference equation for the 2D diffusion equation. Any questions on this? All right. So usually what we like to do, you know, this is usually your first step, but, you know, of course, we usually like to simplify this. Okay. So let's simplify. And so usually one assumption that we'll make, at least when we're first starting out, you know, for our first few problems and our first few codes, what I'd like to usually assume is I like to assume a uniform grid. Okay. And what a uniform grid means is that, you know, we have the same grid spacing in the x and the y direction. So we're going to assume delta x is equal to delta y. And so just to simplify our life, instead of delta x, delta y, I'm just going to say it's going to be equal to delta. Okay. So delta here is the uniform grid spacing. You can't assume this all the time. And so, just be careful using the next equation. Just know that the next equation that I'm going to show is kind of assuming this uniform grid spacing. Okay? But if you have a problem where the grid spacing is not uniform, you have to kind of use the equation above. Okay. But if we can assume a uniform grid spacing, let's multiply both sides by it. And then what we end up is the following. Vi plus 1 comma j minus 2 vi comma j plus vi minus 1 comma j plus vi j plus 1 minus 2 vi comma j plus vi j minus 1 equal to q I comma j times delta squared. Okay. Let's combine like terms because we have two vi comma j's. So let's kind of merge these together. And so if we merge those together, we get vi plus 1 comma j plus vi minus 1 comma j plus vi j plus 1 plus vi j minus 1 minus 4 vi comma j is equal to q I comma j delta. Sorry. And so this right here, this is our finite difference equation for the 2D diffusion equation with the uniform grid. And so before I let you guys go, I do want to kind of label something here, just so that we can kind of start from this next time. Okay. Notice that a big bulk of this equation is a bunch of I plus 1s, I minus 1, j plus 1, j minus 1. Okay. It's really easy to kind of get bogged down in that kind of ij notation. Okay? But there's kind of an easier way to kind of refer to this. Okay? Because whenever you have an I plus 1, j minus 1, that refers to a neighboring node. Okay. And so a lot of times I refer to these I plus 1, j plus 1, whatever, as which direction the neighbor is. Okay. So I plus 1 comma j, that's going to be the neighbor to the right. I minus 1 is going to be the neighbor to the left. J plus 1 is going to be up. And j minus 1 is going to be down. Okay. Upper, lower neighbor, left, right neighbor, upper neighbor, and lower neighbor. Okay. All right, so when we pick this up on Wednesday, we'll do some examples with 2D diffusion, so you can actually see some numbers on this and how we construct the equations. Okay? But the most important thing is, is this kind of switch between the IJ notation and the unique node ID label. Okay? All right, any final questions before we wrap up for today? Okay. All right, so that's all we got time for. So thank you guys for sticking around. I know I went a bit over, so thank you guys for staying a bit. So on Wednesday, we'll pick this up. So hope you guys have a good rest of your day, and I will see you on Wednesday. Oh, yes, thanks for reminding me. Yeah, let me do that right now. Yeah. Mm-hmm. Thanks, you too. Let me upload, go ahead and type it in the chat, Monica, and then, because I'm going to upload the code from today. Yeah, have a good day.
Basically, just splitting up the airflow into two. Just splitting the airflow into two rather than.
The diagonals.
One for each side.
Okay, so the ones, yes. And so actually, this problem here can kind of help with that because, we know the diagonals, the thing about the diagonals is when the row index and the column index are the same, right? And so the off diagonals, the ones, those are going to be, to the left and right of the main diagonal, right? And so if the diagonal entry, if the diagonal entries are, basically B row index. See you guys. Comma row index. The left neighbor. So we're still staying in the same row. So the row index is still going to be the same. Or the first coordinate. And so the left neighbor, you just subtract one from the column. Okay. Remember the second entry here. We have two entries for the matrix. The second entry is always going to be the columns, and so the left neighbor you would subtract one, and for the right neighbor you would add. Okay. And so that's where you would add the ones, and so you would add B row index comma row index minus 1 is equal to 1, and then you have B row index comma row index plus 1 is equal to 1.
I'm not sure if you can hear me.
Yeah, I can hear you.
Okay, perfect. So I did do like these 3 sentences with the +1 and the -1, but this is for the B's. So what is the statement that goes above that? Like if something, then B row index +1 equal 1.
Oh, yeah. So that's when you check if you're in the first or last row of the matrix, right? So you check if row index equal to 1, right? So that's when you're in the first row of the matrix, and so that's when you only assign the right neighbor, and then the last row is row index equal to 5. So that would be the last row of the matrix. Was that what you were asking?
Yeah, because I was doing it 1 to like if row index is like 1 to 4 to do this. Sorry, not 1 to 4. Yes, 1 to 4 to do this, but it was giving me back only the diagonal -2s.
Oh, I see. Yeah, for the if statements, you usually want to stick to just kind of one case in those. So if you're going to do multiple rows, it's best to put that actually in the else statement.
Okay. Okay, I will try again. Thank you so much. Sorry for the inconvenience. Thank you.
Oh, no problem.
Bye.
Bye.